In this video, we're going to walk through some of the calculations that we're doing as part of the CURE project. All of the CURE project is based on titrations. A titration is just a very carefully controlled reaction. It typically involves two species. One is the analyte. That's the solution we'd like to know more about. To do that, we carefully react it with a known amount of a solution we've standardized, which we call the titrant. So we know both the concentration and the volume that we're using of the titrant. So we use the titrant to figure out the concentration typically of the analyte. In the first week of the CURE project, our analyte is a natural water sample, and we're interested in how much calcium carbonate it contains, because calcium is a common component that determines the water hardness of a water sample. To do that, we're using the titrant EDTA. There are actually two different calculations it asks me to do as part of this lab procedure. First of all, it has us approximate the water hardness of our sample using a little instant test strip, and it says based on that, calculate the approximate amount of titrant you will need to add. In any titration, this basically comes down to knowing two different things about each of our components, the volume and the concentration. So for instance, we know how much of our analyte we're going to start with. Let's say we're starting with 50 milliliters. We typically do not know its concentration, but we can estimate it sometimes through the use of a little test strip. So let's say that we performed a little test strip and it approximated that my concentration is about 50 parts per million. And we'll get back to that unit in just a second. For our titrant, we definitely know its concentration. Let's assume in this case it was 10 millimolar. And in this question it asks approximately how much titrant should we expect to add. So we're wondering about the volume of my titrant right here. So in this case we have 3 of 4 missing pieces. And the key to linking them, just like anything else in a chemical equation like this, is relating these species via the moles. So in this case, the mole-to-mole ratio, which very easy in this case, is just a 1-to-1 ratio. So since we have both the volume and the concentration of calcium carbonate, we can figure out how many moles that is, relate it to the moles of EDTA, and then use that with its concentration to find the volume. One issue, though, we have is these somewhat interesting concentration units, parts per million and millimolar. The millimolar is a little easier to deal with because milli is just a metric prefix, and just like anything else, 1 molar contains 1,000 millimolar. So in this case, 10 millimolar is just equivalent to 0.010 molar. So that one's not too bad. The 50 parts per million takes a little bit more effort. First, we need to recognize what parts per million really means. Parts per million means that there's going to be 50 grams of calcium carbonate in every million, 10 to the 6th grams of solution we have. 50 parts per million. What we can do is we can do a little combined conversion in order to get this into molarity, which is a concentration unit we're a little more familiar with. So I'm just going to treat these as two separate little conversions, and I want to get this into molarity, which will be in units of moles per liter. So we just need to convert the top to moles and the bottom to liters. And that's pretty simple. That's two basic calculations. Grams to moles we definitely know how to do. We're just going to use the molar mass. We'll get rid of the grams and turn it into moles. And if we calculate the molar mass of calcium carbonate, in every 1 mole there is 100, that's supposed to be 100 right there, 100.086 grams. So if we do that calculation, we find that it's going to be a very small amount. It's going to be 0.4996 moles of calcium carbonate. Grams to liters we can also do if we remember that since this is a water sample, its density is going to be approximately 1 gram per milliliter. So first we can get rid of those grams and turn it into milliliters, and 1 gram per milliliter. And then we can easily get rid of those milliliters and turn them into liters. So 1 liter contains 1,000 milliliters. So that will give us 10 to the 3rd liters. So we have moles and we have liters, so we can just divide those two numbers, and we find that our molarity is the rather small value, 0.0004996 moles per liter, which we typically just abbreviate with a capital M there. So it takes a little bit of finagling, but we can rearrange this to get these into concentration units that we're more accustomed to. So now what we can do is we can really just rewrite this. Scroll down. So we still here have our calcium. We have our EDTA. We know that's a 1-to-1 ratio, and if we think about the volume and the concentration that we have, calcium, we assumed we're going to start with 50 milliliters. Now we know that its concentration is, and I'm going to write this in scientific notation now, 4.996 times 10 to the negative third molar. For the EDTA, we want to know what volume we need to react, and its concentration is 0.010 molar. Now, this is a little bit easier because we know in general that molarity equals moles divided by liters, so it's very easy to relate these two things. Again, we're going to relate these via the moles here. So we have to start with the calcium carbonate since we have both the volume and the concentration of that one. So if we rearrange our molarity equation here, we know that moles is equal to molarity times volume. So here we have milliliters. If we rewrite that into liters, that's going to be 0.050 liters. So our molarity, 4.996 times 10 to the negative third molar, times our volume, 0.050 liters, excuse me, is going to give us 2.498 times 10 to the negative 5, times 10 to the negative 5 moles. So again, a very, very small number of moles. Scroll down a little bit here. So now we know how many moles of calcium carbonate we have, 2.498 times 10 to the negative 5 moles. And since this is a 1-to-1 ratio, now we know that we have 2.498 times 10 to the negative 5 moles of EDTA as well. So that's how many moles of EDTA we're going to need to add in order for this titration to reach completion. Now what we want to do is turn that into a volume. So if we again rearrange this equation right here, the volume in liters is equal to mole divided by molarity. So now we have this number of moles, 2.498 times 10 to the negative 5 moles, over the concentration, 0.010 molarity. And if we do that division, we get still a pretty small number, 0.02498 liters of EDTA that we're going to need to add. But of course, if we're using burette in a titration, we'll just turn this into milliliters. So that's going to be 2.498 milliliters that we are expecting to add. So it's a little long, but most of that is because our original concentration was not given in these nice friendly molarity units, but instead given in those parts per million, which makes this a little more difficult. This was an example of the first type of calculation it asked us to do. And you might say, oh, this is only the first, I have more to do. But it's really not so bad because all of the calculations are going to look like this. The only difference is going to be which one of these 4 pieces we're going to be missing. So this is the calculation that we do before the titration starts. So we can estimate how much of this EDTA we need to put in, and that will help let us know if our calculation, if our titration is going well. After we do the titration, what we'll do is we'll say, now we know exactly how much of this we poured in, and we're going to get a better estimate of this right here. So this 50 parts per million was an approximation that we got from a quick little test strip. After we do the actual procedure, now we're going to figure out exactly what that concentration is. So again here we still have my calcium carbonate and we still have the EDTA and we have a volume and a concentration. We still started with that 50 milliliters of the calcium carbonate, and we still know that we are using the 0.010 molar EDTA. Let's say we do the calculation and we find that we poured in exactly 3.25. That's a 3 right there. Let's go back and rewrite that. 3.25 milliliters. So a little more than we were expecting. So we want to know exactly what our actual concentration was. So that 50 parts per million was just an approximation. Now we want to know the actual number. So again, all we need to do is we need to relate these via moles. That's it. So we're going to relate these via those mole-to-mole ratios. In this case, it's these two on the EDTA side where we have both pieces of information so that we can turn these into moles. That'll tell us moles of calcium carbonate, and then we can use it to get that concentration. So again, we know that molarity equals moles per liter. If we want the moles, it's going to be molarity times liter. So in this case, for the EDTA, our molarity is 0.010 molar. Those 3.25 milliliters, if we turn that into liters, gives us 0.00325 liters. So if I do my math, then I get you know what, let's do scientific notation. That's going to make my life a lot easier. So if I do the math on that, I get 3.25 times 10 to the negative fifth moles of EDTA. Since, again, this is a 1-to-1 ratio, that means it's also equal to the moles of calcium carbonate. So now I have my moles of calcium carbonate and I have my volume of calcium carbonate, so I'm going to put them together to get the concentration. And in the procedure, it specifically wants it in, again, this interesting unit of parts per million. So what I have right now is 3.25 times 10 to the negative 5 moles, and I know that that's in 50 milliliters. In parts per million, to get this into parts per million, I need to turn both of these into grams and then multiply by 1 million. So again, we're going to do that sort of split conversion. We'll do one piece at a time. On the top, I'm going to turn my moles into grams. So I know the molar mass is 100.086 grams. That's an 8 right there. Grams per every 1 mole. So I'll do the math on that. On the bottom, I'm going to again use the density, so we're just doing the reverse of the calculation we did a little higher up. Again, the density is 1 grams per milliliter, so that one's easy. I'll have 15 grams. So I'm running out of room here, so I'm going to just move that down there. So if I do this top part, I turn my moles into grams. I find out that I have 0.00325 grams of calcium carbonate. And on the bottom, I know that now I have 50 grams, and this is of the whole solution. So to do parts per million, all I need to do is divide those, and then I take that answer and multiply by 1 million, which is equal to 10 to the 6th. And in this case, I get 65.1, and now my units are ppm. So our test strip predicted it would be 50. We can see it was actually a little bit higher than that, 65, but that's why we did the actual titration, so we could get a more accurate answer. So all of our titration questions are going to look like this. We'll have two things that we're trying to relate. We'll have volumes and concentrations, and we'll always have 3 pieces, and we'll just be missing 1. Usually, initially what we have is the volume of the analyte and an approximate concentration of the analyte that we can get from a little quick test, and the concentration of the titrant. And initially we try and calculate how much of the titrant we need to add. Then we actually do the titration. After we've done the titration, we have this exact volume, and we try and go back and get a more accurate representation of our analyte concentration. So not just a quick test, but the titration gives us a much more accurate number, which in this case was 65.1 parts per million.